Okay, so welcome to Math 150 Multivariable Calculus. This is lecture 29. We are on the home stretch. What I want to do today is a mix of theory and application. What we're doing is, techniques of integration. And in multivariable calculus, it's a little bit easier than one variable calculus. We really only have two techniques. We can switch the order of integration. And if you're doing a double integral, there's only two options. And we can do change of variables. And there are certain natural ones, the polar, the cylindrical, the spherical. What I want to do is talk a little bit about what do you do when you can't actually integrate something in closed form. Now, a lot of times you think you can do things that you can't because of how it's been shown to you. So what's the derivative of cosine? Negative sine. What's the derivative of sine? Cosine. And that's only true if you're working in radians. If you're working in degrees, you have this annoying factor of 2 pi over 360. This is one of the reasons why we use radians, because then the derivatives of sine and cosine are essentially going to each other. How do you calculate the sine or the cosine of a number? Calculator, right? How does the calculator do it? So it's Taylor series. Now, there's a couple of nice numbers we can do. What are the nice triangles? I'm sorry? 30, 60, 90. Where does the 30, 60, 90 come from? So when we're doing derivatives of sines and cosines, derivative of sine of x is cosine of x. Derivative of cosine of x is minus sine of x in radians. Compute by Taylor series or identities from nice angles. And you said we have the 30, 60, 90 triangle. Where does the 30, 60, 90 triangle come from? How do you know what the sides are for the 30, 60, 90? But so how do you know, why is it, if we make this 1, why is this over here 1/2 and this root 3 over 2? So you said it's a nice triangle, but you would need to know one of the sides. I don't want a circular argument, especially dealing with circles. I'm saying, why is it 1/2 and root 3 over 2? I agree that if you give me one of the sides, I can get the other. But you have to be able to give me something. So there is an easier triangle to work with than the 30, 60, 90. Okay, so if we do the 45, 45, 90, this one is a little bit easier. So now, if this is 1, if this is x and this is x, by Pythagoras, we get 1 squared is x squared plus x squared. So 2x squared equals 1. So x equals root 2 over 2. So for the 45, 45, 90 triangle, I agree that we can solve it by using Pythagoras. I agree. But for the 30, 60, 90, if I call this, x and I call this y, I just get 1 squared is x squared plus y squared. That's not enough to get the sine or the cosine of 30. So where does the 30, 60, 90 triangle come from? It's got to come from a triangle where we know all the sides. If I draw the triangle maybe like this, yeah, it's half an equilateral triangle. So we do like this, 30, 30, 60, 60. Now, if this is 1, this is 1, if this whole thing is 1, each of these have to be 1/2. And so now if I call the side y, I would get 1 squared is 1/2 squared plus y squared. So 3/4 square root is equal to y, or y is equal to root 3/2. So we can figure out the 30, 60, 90 triangle because we know the equilateral. These are the only two triangles we know, where we know the angles and the sides. And now if you want to calculate what's going on in all other places, all I have to do is I can use my trig identities. I can now use double angle, half angle formulas. If I want to write something, I can write it as a bunch of movements. And so this is kind of similar to a divide and conquer. I can start having like this infinite chain. You know, if you want to give me something like 10 degrees, can I get 15 degrees? Well, let's see, I can do 30 degrees, I can do 45 degrees. Okay, I should be able to do then 45 minus 30, I can do 15 degrees. I can do half of 15 degrees, which would give me 7.5. Then I could add half of 7.5 to 7, and I'd be a little bit over 10. Then I subtract a little bit, and I can do this infinite hop game. And so if I wanted to calculate sines and cosines, yes, I can do it like that. But this is going to be bad, and it's going to be an infinite process in general. And so what we typically do is we use the Taylor series. So e to the x is the sum, n goes from 0 to infinity of x to the n over n factorial. This is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. We have e to the ix is cosine x plus I sine x. And we'll get, cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot, dot, dot. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot, dot, dot. Just because I write down names for these functions doesn't mean I can calculate them easily. Now, these series are very rapidly convergent. And I think we might have seen some animation early in the semester that if I just take a couple of terms, I can get a terrific approximation for these functions. But just because I've given them a name doesn't mean we really understand them. We now just have a button on the calculator that we push and it will compute it for us. But it's doing an infinite series. It's doing an infinite series that is so important and so common, we give it a name. We give it the name cosine or the name sine. But it's an infinite series that we have to deal with. And so the question is, what other things can we deal with? It turns out in probability, there's some very important functions. We saw this in baseball. F of x is a density if two things hold. F of x is greater than or equal to 0, and the integral from minus infinity to infinity of f of x dx equals 1. You could, of course, have a discrete probability. You could have a probability that's a mix of two. We'll deal with continuous probability distributions. We say the cumulative distribution function is the probability that you're at most x. So it would be the integral from minus infinity to x of f of t dt. And we'll just call that big F of x. Okay. So this is an extremely useful quantity to compute. It's the probability you get a value at most this large. So we need to compute this. So has anybody here taken stats? Okay. What is probably the most important distribution in statistics? The normal, right? The normal, the bell curve, the Gaussian. When you have this many names, you are important. So we say a normal with mean mu and standard deviation sigma is the following. Its density is f of x is 1 over the square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. And so if you plot this, it's centered at mu, it's symmetric about that. and then just how quickly it decays is going to be related to sigma. So the smaller sigma is, the tighter it's going to be. This is one of the most important densities in all of mathematics and all of science. So many things converge to being normally distributed. If you look at like distributions of heights, it's often normally distributed about the mean value. So it might be interesting to know what's the probability that if you have something that's normally distributed, you take on a value at most x. To make life simple, what do you want to choose from u and what do you want to choose for sigma? Just to make life simple. 0 and 1. So let's try to do a special case. Let's try to find the probability that we're at most x. So we want the integral from -infinity to x, e 1 over square root of 2 pi, e to the negative t squared over 2 dt. So we want to calculate this. So does anybody know a function whose derivative is e to the negative t squared over 2? Is there a nice closed form antiderivative? So unfortunately for this case, there is no nice antiderivative. Now, other functions, if I gave you the natural log of t, it turns out there is a nice antiderivative for natural log of t. For this one, there is nothing. Does anybody know any nice formulas for the exponential? Any formulas for the exponential of a number? Any way to calculate the exponential of a number? Yeah, the Taylor series. Why don't we just put that in? The integral from -infinity to x of, I'm going to drop the 1 over square root of 2 pi. We can just multiply by that at the end. We have e to the negative t squared over 2 dt. This is the integral from -infinity to x. And then it'll be the sum, n goes from 0 to infinity, of negative t squared over 2 to the n over n factorial dt. This is essentially like a double integral. Instead of having two integrals, I have an integral and a sum. What would you like to do to the integral and the sum? Yeah, just switch the order. So let's switch the order. So if we switch the order, what I can do is I can pull out a lot of things. So it's going to be a sum, n goes from 0 to infinity. I'll get a -1 to the n. I'll have an n factorial 2 to the n down below. And I'll have the integral from -infinity to x of t to the 2n dt. Oh, that's not a bad integral to do. I now just need to find a function whose antiderivative is t to the 2n. So can anybody give me a function whose, I'm sorry, I need a function whose derivative is 2 to the n. What's the antiderivative of t to the 2n? So what function has derivative t to the 2n? So what function, when you take the derivative, do you get e to the 2, do you get t to the 2n? So let's do a specific example. If I give you t to the 4th, what function has a derivative t to the 4th? I'm sorry? T to the 5, t to the 5 over 5. What if I gave you t to the 10? Okay, so what if I give you t to the 2n? Nope. T to the 2n plus 1. I increase the exponent by 1. And what do I divide by? 2n plus 1. I evaluate this at x and infinity and negative infinity. Oh dear. So I get the sum, n goes from 0 to infinity, -1 to the n factorial 2 to the n. Oh crap. I'm now going to have x to the 2n plus 1 over 2n plus 1 minus infinity, I'm sorry, minus negative infinity to the 2n plus 1 over 2n plus 1. We can't do this. I can't just switch the orders of integration, and just, go through this, because now I've got this infinite term. So the question is, how would we handle something like this? If you look at this function e to the negative t squared over 2, so I'm going to plot it for you. This is essentially my density. I claim that there's one value of x where you should know what the answer is. And if you want to, I'll put in 1 over the square root of 2 pi. If I put in 1 over the square root of 2 pi, what does it integrate to? If we go from negative infinity to infinity. Nope. So I've put in the 1 over square root of 2 pi. There's one value of x where we know this. What's the one value of x where we know the answer? Where we know this integral, or there's 2 values of x we know. Good, what's the answer? Nope. A half. And what's the other value where we know it's equal to 1? When x is infinity. This is a probability distribution. We said a probability distribution has 2 conditions. It's non-negative, and the area under the curve is 1. So if I take x equals infinity, I'm saying I'm going from minus infinity to infinity. What's the probability I take on a value that's the most infinity? It's 1. So we know the answer when x equals infinity, but we also know the answer when x equals 0. This is a distribution that's symmetric about 0. So if it's symmetric about 0, the integral on the left half is the same as the integral on the right half. And so what do those have to be? They both have to be a half. So we know the answer is 1/2. Okay? So there's one value of x where we know the answer, one finite value of x where we know the answer. If x equals 0, what does this have to equal? It has to equal 1/2. So what we can do is we can do the following. Let's say we want the integral, say 1 over square root of 2 pi minus infinity to x of e to the negative t squared over 2 dt for x greater than 0. You can do it very similarly when x is less than 0. Okay, we can write this. It's 1 over square root of 2 pi integral negative infinity to 0 e to the negative t squared over 2 dt plus 1 over the square root of 2 pi integral from 0 to x e to the negative t squared over 2 dt. What does this first integral equal? A half. So now it's very similar to before. 1 over square root of 2 pi, the sum n goes from 0 to infinity, negative 1 to the n over n factorial 2 to the n, t to the 2n plus 1 over 2n plus 1 at 0 and x. Oh, wait, that we can now do. Because now that we have a 0, we don't have to worry about the bottom term. This is just going to be 1/2 plus 1 over square root of 2 pi. The sum n goes from 0 to infinity of negative 1 to the n over n factorial 2 to the n x to the 2n plus 1 over 2n plus 1. So there is something very close to this that's called the error function or the ERF function. The only thing that changes is instead of e to the negative t squared over 2, I think it's just e to the negative t squared or something along those lines. It's a little bit of a tweak as to which is the integral that's easy to do. What I want you to see from this is a couple of points. One, probability distributions are extremely useful, but they're often very hard to calculate integrals in closed form. The standard normal, the Gaussian, this is one of the most important distributions. We can't write down in closed form what it is. There's no function that's simple that has derivative e to the negative t squared over 2. We can try to integrate term by using a series expansion. Unfortunately, to do this, we have to switch an integral and a sum, You can't always do this. So, we talked about Fubini's theorem earlier. We talked about switching orders of integration, and I gave you this cooked up example with an infinite lattice of plus ones and minus ones. And you can say, okay, that's a pure mathematician being a pure mathematician, but do I really have to care about this in the real world? Yes. If you want to do statistics, if you want to work with things like the normal distribution, you would love to switch orders. We can't do it here. It all breaks down. Now, fortunately, in this case, and this is one of the hardest things to learn, if you look at problems the right way, you can often make progress. And here the trick is, well, what was causing trouble? It was going from minus infinity. If we just go from 0 to x, everything is fine. And so we know the answer from negative infinity to 0 is just 1/2. So if we put that in, then we just have to integrate from 0 to x. If x was less than 1/2, you would then subtract off the integral from x to 0. And so we can now come up with this infinite series expansion. We can create a new function. We can give it a name. And something very close to this is called the error function. You might think that this is a bit of a cheat, but we've already done this with cosine and sine. That's why I started the class by discussing cosine and sine. Cosine and sine are really infinite series. For a couple of special values, we can cheat and we don't have to use the infinite series. These are the values coming from the 45, 45, 90, or the 30, 60, 90, which is really coming from the equilateral 60, 60, 60 triangle. But really, for sines and cosines, we're doing an infinite process. But it's been standardized and accepted. Oh, it's not a big deal, it's just the cosine function. We can keep introducing more functions. We just want them to be useful. We want them to converge quickly. This is another example of something that will converge quickly. All right, so hopefully what you saw from this is just how difficult it can be to do the calculations we want to do. Okay, any questions on this before we move to the next part? All right, so in a lot of the rest of the semester, we're going to focus on integration techniques in several variables. What I want to do now is I want to talk about a beautiful way to calculate integrals by playing dots. And so if this was an old building, I would actually bring the dot board down and we could actually throw dots and do the experiment. If people want, you can come to my office. Given that this is a new building that's supposed to last us a while, I don't really want to have the dots flying, hitting the walls. But imagine, so this is called Monte Carlo integration. So for simplicity, let's imagine we have a box that's a square that's 1 by 1, and we have some region, A, that's inside this square of side length 1. And what I'm going to do is I'm going to randomly throw dots. And let's assume each dot is as likely to land in any spot of the square as any other. It doesn't have to be a square. I could do a rectangle. I could do a cube in higher dimensions. Let's just do a square because my art is horrible. Okay, so what we do is we throw a bunch of dots. And so let's say we throw n dots. And we estimate the area of A should be approximately equal to the number of hits, these are things inside A, divided by the number of tosses. If you, yes. Sure, so we see how many times does our toss land inside A? And we divide by the number of tosses. So let's say that A has area 1/2, and the whole thing has area 1. So if A has area 1/2 and every part of the square is as likely to be hit as every other, then I should land in A half the time. If A has area 1/3, then I should land in A 1/3 of the time. And so the more dots I throw, the more accurate this should be. If you toss a coin once, what are the probable outcomes? Heads or tails? Is there any other possibility? Yeah, we're going to assume the coin is not going to land on its side. So we will assume the coin lands either as a head or a tail. When you toss the coin once, what are your estimates for the probability of a head or tail? 1 and 0, right? If you toss the coin 2 times, what are the possible estimates you could have? And now you could have half. And if you toss it 3 times, it could be 0, 1/3, 2/3, 1. The more times you toss, the more possibilities you have for your estimate. And the more likely you are that your estimate will be close to the true value. If your coin is 80% heads, if I toss it just once, I'm going to get 0 or 1. If I toss it twice, I can get 0, 1/2, or 1. The more times I toss it, and this is the central limit theorem, this is the big result from stats and probability. If I look at the number of heads divided by the number of tosses, that should converge to the probability of a head. So again, we are in pre-registration now. You should be thinking about what classes do you want to take after this. Statistics is an excellent class to take after this. And you would talk a little bit about how would you estimate the probability of a coin? Well, if I flip the coin a huge number of times and I record how many heads and I divide by the number of tosses, that should be a pretty good estimate for the probability of a head. And the more times I toss it, the better estimate it should be. It's the same thing here. I throw the dots uniformly in the unit square. And I record how many times do I land inside A, and I divide by the number of tosses. And that should converge to the area of A as I do more and more tosses. Well, if I wasn't 1 by 1, I would then have to just rescale things a little bit. So if it was more generally, it could be A divided by, say, the rectangle. And then that would converge to the number of hits inside A divided by the number of tosses. Yes?
When you have to assume that every darter is going to land within the larger board and the person throwing it has a chance of hitting everyone.
Yes. Yeah. Yep. We are making those assumptions. Yep. We're assuming that every toss lands in the rectangular region and every spot is as likely to be hit as every other. Who here has watched The Big Bang? Oh, this is so sad. Big Bang Theory. Oh, no. I'm assuming nobody here is as old as I was around when The Big Bang happened. Yeah. I know I'm older than you. The Big Bang Theory, the TV show. How many of you have seen that show? Clips. Oh, this is sad. Do you at least know who Sheldon is and what kind of personality he has? Okay. So there's an episode, I think he's on his honeymoon when he is talking with his wife and they start talking about random number generators. And he becomes very excited because she says there's no such thing as a truly random number generator. He's so excited that she understands this. It is a real question. How do you choose things randomly? There is a beautiful article, if people are interested, I can try to find it, of a, I think, Canadian geologist who found that there was a scratch lottery in Canada that wasn't entirely random. And he alerted the lottery to this and they said, and they ignored him. He then sent back 20 tickets and told them how to scratch. And he was right 19 out of 20 times. And all of a sudden they started listening to him. Is that they had made a small mistake and it was not entirely random and you could crack things like that. There's a lot of examples of people trying to do things randomly and they make small mistakes and you can often exploit this. When I am saying we choose our points randomly in the region, how? That's not necessarily an easy thing to do. There are ways to approximate choosing points randomly. Let's assume for the sake of argument that we can do that. Then, the theory says that this will converge and we can even talk about how quickly the fluctuations will be. Error is on the order of 1 over square root of n for the probability for the area. So if I do 100 tosses, I would expect to be on the order of about 10% off. If I do 10,000 tosses, I would expect to be within about 1% of the area. It might be twice that, it might be a half that, but on the order of 1 over square root of n. And this is basically from the central limit theorem. if you know what that is. Okay. Let's do an example. What I'm going to do now. Okay. So hopefully people can see this. Yes. So what I've done is I have a region. I've chosen a couple of points. The red points are inside the region, the blue points are outside the region. Anybody want to guess what region it is? Or do we not have enough data? All right, so and then over here, I'm going to record, I think, what fraction of the points land inside the region, and I get 3.2. So hopefully this will work. And then as soon as you figure out what it is, just shout it out. Oh, yeah. Wow, it moved really fast. It's supposed to go quite slowly. I told it to go on the slowest possible speed. All right.
What's 3.2? Is it 3.2 out of what?
It's estimating the area. So the square has area 4. So it's looking at the area of the region divided by 4 should be the fraction of the points inside. So if you take the fraction of the points inside and multiply by 4, that should be the area of the region. All right, so it's not working well right now. All right, so here I'll do it manually. 10 points. Well, not quite 10, but. And you can see as I'm adding more and more points, it's starting to fill in very quickly. So, okay, so here is a bunch of random points that I've chosen. I'm getting 2.99. When you look at these points, do you think that these points were randomly chosen? Yeah. Do you think they were chosen randomly and uniformly throughout the whole region? Why not? Yeah, there's some clustering. So here's my question. How many of you have randomly chosen 10,000 points inside a square? You have no experience doing that. Should there be clustering or not? Imagine you were to flip a fair coin 100 times. How many heads would you expect? 50. And then the central limit theorem from statistics would tell us what scale our fluctuation should be. But here's the question most people have no intuition for. What should be the longest run of heads when you flip 100 coins? How many alternations should you have between heads and tails? There's a lot more refined statistics you can do. Did anybody ever read Rosencrantz and Guildenstern Are Dead? Okay, what am I thinking of? What scene? They're flipping a coin and they've had over 90 consecutive heads. And I won't give away what happens in the end. You have to read the book. Any string of tosses is as likely as any other string of tosses. If I give you a sequence of heads and tails, that's as likely as any other sequence of heads and tails. But if you look at all possible sequences, I would be shocked if I wasn't close to 50-50 heads tails. And the more tosses I have, the more shocked I would be if I'm not close to that. Yes.
If you have any number of runs or tosses or whatnot, what is the probability of getting a single kind of run be 0? If we have a
Well, the more tosses you have, the more possible strings you have, and the lower probability any specific string has. But you could then say, what's the probability that the percentage of heads is within 1 of 50%? The more tosses you have, the greater the chance it is that you get a string that's within 1% of 50. The fewer tosses you have, the more likely it is that you would have something that's far away. So again, each string is as likely as every other, but when you have a tremendous number of strings, with extremely high probability, whatever string you take will have roughly 50-50 heads tails. And we have more refined statistics we can look at in terms of the run of heads or the alternations between heads and tails. And we can use stuff like this to detect with high probability, has someone fudged data? And so I've done a lot of work over the years using other kinds of tests to see if data has been fudged. So the problem is when you have something like this, it's actually not unreasonable to have gaps like this and to have clustering. Is you would expect to have some level of clustering when you do this. And the problem is you could be a little bit unlucky. Maybe my region is a circle where somebody took a hole punch and punched out something over there. And as an example of where that could happen, I lost, I think, 7 or 8 hours of my life due to Verizon. I don't want to go into too much detail because this is being recorded. In the end, one of the compensations was an upgrade for my daughter's phone. She got a plastic case and she had me print out some patterns that you would just put in the back. And now she could just, since it's a clear case, you could just change which pattern she has. What does she have to do to the rectangle that you printed out? I'm sorry? Okay, but in particular, she has to cut out the camera part. So originally, I was a nice dad, and I did 2 different things so it was double-sided, so she could just flip it over. And she was very happy that she was, oh wait, we have to cut off for the camera, and it's not going to be the same on both sides. So we would have to actually cut off 2, so it's not going to work. Why am I bringing that up? Well, if I happen to have a region like that, it looks like maybe it's a rectangle or an oval, but there's that little corner that's missing for a natural reason. And so if you happen to be unlucky enough to have a cluster issue there, where you're missing points there, or maybe you're overly sampling points there, then you could get a bad estimate. Now, as you take more and more points, the error from this is getting smaller and smaller and smaller. But this is how a lot of integrals are done in the real world. It's just too hard to evaluate in general. So what we do is we just randomly sample. And for a lot of functions, it's actually very easy to say, am I inside the region? So we're going to be talking about simple regions. And your simple regions, if you're X simple, you enter, stay in, and then leave. So you have like a lower boundary and an upper boundary. And all I have to do to tell if I'm in the region is I have to say, hey, am I greater than the lower boundary and less than the upper boundary? If yes, I'm in the region. So I don't need to find antiderivatives. I just need to do some simple algebra. Am I in the region? Stuff like this, however, does have issues with gaps. Anybody have any thoughts as to how we could get rid of these issues with gaps? What could we do? So is there any way to choose points so I don't necessarily have these gaps? Or the region, but how should I choose my sample points so that I decrease, having giant clusters like this showing up where I have no sample points? Yes, I could space them out. I could use a lattice. When the pandemic hit, I tried to convince school districts to have kids sit in a hexagonal lattice, because that would actually maximize being 6 feet apart and how many people you could get in, rather than using the standard rectangular lattice. If you know how many points you're going to use, if you know I'm going to have 10,000 points, or I can do 100 by 100. The problem is if you do 100 by 100, and then all of a sudden you find out, actually, we can run the program for another 7,000 or another 200 or whatever points, where do we put those in now? And so one possibility is you could just say, look, I'm going to do 10,000 points. I'm going to do it in a lattice, and that's going to make sure I don't have any biases like this. It's going to spread things out uniformly. But unfortunately, if I then have additional runtime, how do I put in those extra points? there's a problem then if you have additional time. But if you know precisely what you're going to do, it's a really good way to do it. And it tells you that certain numbers would be better to use than others. Numbers that have nice square roots would be very nice. Powers of 2 would be terrific. Rather than doing 1,000 by 1,000, I'd probably rather do 1,000. Who knows their binary? 1,024 by 1,024. So again, when you're doing implementation issue, these are things to think about. All right, let me just try to get the next one set up. Okay. All right, anybody want to guess what this region is? I'll do some more points, and it's 0.8. 10. And so still nothing. Still nothing. Any thoughts? An ellipse. Excellent. And so this is an ellipse. And when I look at this ellipse, what am I seeing? I'm seeing 1.52. And so if I look at this ellipse, let's see if I can actually draw here. No, I can't. All right, so I will switch back and take the screen. So we had something like this, where it was minus a half, 1, minus 1. The area was approximately, I think, 1.52. Anybody have any guess as to what 1.52 might be? It's close to half of pi. So an ellipse is x over a squared plus y over b squared equals 1. Now a circle, you can write as x over r squared plus y over r squared equals 1. The area is pi r squared. What might you guess the area of an ellipse is? So the area of the ellipse has to reduce to the area of a circle when what happens? When a equals b equals r, we have to get pi r squared. What might you guess the area of an ellipse with semi-major axis A and semi-minor axis B? What might you guess? So you could try a plus b over 2. You'd probably have to square that. So that would work. Can anybody give me another guess? Something else that would reduce to pi r squared when a equals b equals r. So one possibility is a plus b over 2. There's something else that will give you pi, I'm sorry? Well, a squared over b squared if a equals b. Oh, okay. So if you do a squared or b squared, then that means one of them doesn't matter at all. So that means if I fix a and I change b, I'm not going to change the area. So while that would reduce, it's not going to reduce properly. It should probably depend on a and b. So how can you take your answer and tweak it a little bit? Not pi a squared, not pi b squared, but pi ab. that would also work. Now we know when A equals 1 and B equals 1/2, we seem to get 1.52, which is about pi over 2. So if we look at what we have over here, A equals 1, B equals 1/2, this would give us pi 1 plus 1/2 would be 3/2, 3/4. So that would become 9/16. And this would become pi times 1/2. And I'm going to write 1/2 as 8/16. So the two answers differ by 1/16. So this data is not refined enough. It's not sharp enough to tell the difference between the two. But as we get more and more data, there is a significant difference between 9/16 and 8/16. We could also take values of A and B that maybe differ by more to make it more pronounced. It turns out that the one that's correct is this one. It's pi AB that reduces to the right answer. Although A plus B over 2 works as well. If you've seen the arithmetic mean, geometric mean, if that means anything to you, that's essentially what's going on in the background. But we can start to sniff out formulas by doing some numerics like this. And as we do more and more numerics, as we get more and more data, what I'm going to do is I'll just go back to this. And if I go up all the way to the end, I'm getting 1.56. That's looking pretty good. So the last thing I want to do, we've got about 2 minutes left, is talk about what could we do where I want to put the points coming in somewhat randomly. But if I have more computational time, I wanted to be able to run it longer. If I do a fixed lattice, a fixed square lattice, that's great. I'm going to have the points uniformly spread out. I'm not going to have any big gaps in my region. But if I can then run things a little bit longer, I don't know where to put things. I could maybe try to start filling in regions between the dots, but I might not have enough to fill it in all the way. I don't want to go through all the details. I just want to show you a little bit what's out there mathematically. You can use the Fibonacci numbers. And so, what I will do is I'll go all the way back to the beginning. I'll try to go all the way back to the beginning. And then what I'm going to do is just slowly add more and more points. And hopefully this will work this time. Okay, now it's going slowly. And so it's adding more points, and it's using essentially the golden mean and the Fibonacci numbers in terms of how it puts them in. And it's basically filling it up. But what do you notice seems to be happening? What do you notice about these points? Not quite uniform, but there does seem to be a lot of, what do you seem to notice about them? Yeah, there's a bunch of lines. And the lines don't entirely match up. And so very, very slowly, you start to add more lines, and it will start to speed around. So if I just jump forward a little bit in time. I'll jump forward by just speeding things up. Hopefully. And you can see it's just not quite aligning. And so because it's just not quite aligning, it is slowly going to start filling things up. And so what's great about this is you just run it as long as you can. And it's just putting in the points. And so this is just a great example of how pure mathematics can come in for a very applied problem in terms of doing computations like this. This is the 21st century. You've got to do computations like this. All right, so this is a good place to stop. And again, the point of today was to give you an application of what we're doing. You're not going to be expected to do anything like this on an exam, but I want you to be aware of various techniques and methods.